Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video I'm going to cover electrophilic addition of conjugated dienes. We're going to go through a couple examples of this, and by the end of it you should be able to understand 1,2 and 1,4 addition without even having to remember that 1,2 and 1,4 addition exist when you're doing these electrophilic addition reactions. Before you watch this video, I highly suggest watching the video Alkene Addition Reactions, at least from the beginning of it through the Understanding Hydrohalogenation section of the video. And of course, any videos that are recommended in that video, if you haven't watched them already, you should probably watch those as well, as they are prerequisites to really understanding how this reaction works. Let's start by reviewing an electrophilic addition of the simplest conjugated diene that there is, 1,3-butadiene. We always start with our problem-solving process before diving into the reactions, so we're going to make a list of everything we know about this conjugated diene. Well, first, we know that it is a conjugated diene, and conjugated dienes are really just like alkenes. Now, they're a little more stable than alkenes. However, for the most part, most of the reactions we can do with alkenes, especially the additions, we can also do with the conjugated dienes, and that's because those pi bonds are electron-rich, which means they're both nucleophilic and basic. So we have those nucleophilic and basic pi bonds. So for the most part, we're going to say we can do addition reactions with them. Now, that's not the only reactions that we can do with conjugated dienes. Usually, when you first learn about conjugated dienes, you also are introduced to pericyclic reactions. So we can also do pericyclic reactions. Usually you learn about the Diels-Alder reaction when you first learn about conjugated dienes, which is one type of pericyclic reaction. However, there are other pericyclic reactions that some textbooks teach you around the same time. Next, we look at the second reactant, and that is an acid. So it looks like we have that nucleophilic and basic pi bond, and we have an acid. So what's most likely going to happen is we're going to react that pi bond with that acidic hydrogen. So now we can move on to step 3 of the problem-solving process, which is draw the mechanism. And as usual, when we draw our mechanism, we draw an arrow from the region of high electron density to the region of low electron density, or in other words, from negative to positive. So which pi bond should we draw the arrow from? Well, in this case, since this molecule is symmetrical, it doesn't matter. Each one will do the same thing. So we're going to draw our arrow from the pi bond to the hydrogen, and that's going to break the hydrogen-bromine bond. And as usual, whenever we're reacting a double bond with an acid, we're going to generate a carbocation. And the carbocation always goes to the more stable position. Now I'm going to draw that hydrogen here in blue, just so we can keep track of where it went to. But the carbocation goes to that secondary allelic position that we have there, because the allelic position is way more stable than that primary position, so of course we're going to put the carbocation in that spot. Anytime we generate a carbocation, we have to check for resonance, carbocation rearrangements, and in our final product, stereochemistry. With the intermediate, we do have resonance to worry about, so we can actually draw a resonance structure for this. And that, I'll draw the arrow pushing in green, and then I'll erase it. That's going to give us a resonance structure that looks like this. And once again, I'm going to draw in that hydrogen that I originally added in blue so we can keep track of where it was. So now that we have the resonance structures drawn, let me erase this green arrow so I can show the next step in the mechanism. And the next step of the mechanism is we take that bromine that we kicked off in the first step, and the negative charge on the bromine can attack that carbocation that we have. And we have two pathways here because of this resonance structure. So I can draw my arrow from my excess electrons on the bromine to that positive charge, and we can do that on the bottom resonance structure as well. And that's going to give us two different products. And I will draw that bromine in blue next to the hydrogen. In the bottom structure, we have the same idea, where we add the bromine to where that carbocation was, and again, I'm going to draw that in blue so we can keep track of our two addition products. Of course, the last step in the problem-solving process is to check your work by considering anything you might have missed, such as a resonance structure in the intermediate, or a carbocation rearrangement in the intermediate, or stereochemistry in the final product. So if we look at that top product, notice that there is a stereogenic center on the carbon bonded to that bromine, which means when we added that bromine on, it could have been added on a wedge or on a dash because we had a trigonal planar carbocation. So that means we do have to worry about including whether it's a wedge or a dash, so we'll use the squiggly line indicating that it could have been added either way. On the bottom, we don't have R or S stereochemistry to worry about. However, we do need to worry about E and Z stereochemistry, and the reason why has everything to do with the fact that we're moving around that double bond via resonance. Although the conformer that I'm drawing is higher in energy and therefore less stable, it is possible that when the bromine attacks, the carbocation just might happen to be rotated in that position. That's going to give us the minor product, which is the Z isomer. Now, some textbooks and some professors do not emphasize or even mention the Rns stereochemistry or the E and Z stereochemistry involved in these reactions. However, some do, so I wanted to make sure I covered it just in case this is something that your class requires you to know. What is covered, however, by pretty much every single organic chemistry class is the 1,2 kinetic or the 1,4 thermodynamic products that can be formed in this reaction. I have been showing the atoms that we're adding onto the double bond in blue. And the reason why is I want to really show where these things are being added. In the first step, we add a hydrogen to the double bond. And where the hydrogen gets added, we are going to arbitrarily label with the number 1. Where we add the bromine, of course, depends on which pathway we take. But if we label the carbon next to that first carbon as the 2, we can see that this top pathway gives us what we call the 1,2 product. On the bottom pathway, we can see, if we again label where the hydrogen was added as carbon 1, we can see that by the time we count over to the bromine, we add it to the 4 position. And that's why these are labeled as the 1,2 and the 1,4 products. In this video, I'm not going to go into too much detail regarding the kinetic and thermodynamic products. However, I will mention the basics. We will get a mix of both of these products when we carry out this reaction. The kinetic product is formed faster due to the proximity of the bromine anion to that 2 position as soon as the HBr bond is broken, and due to the lower activation energy needed to form its transition state. The thermodynamic product is more stable due to the greater substitution of the double bond in the final product. If you look at that 1,4 product, it is di-substituted in the 1,4 versus mono-substituted in the 1,2. But this product forms more slowly due to the higher activation energy needed to form its transition state. The kinetic product is going to be found in greater concentrations when we carry out this reaction at lower temperatures, while the thermodynamic product is found in greater concentrations when it's carried out at higher temperatures. Now that we've gotten the simplest example out of the way, let's add some layers of complexity. Here we have another conjugated diene, so again it acts like an alkene, and we can do addition reactions with it, and we have an acid. So this reaction is going to proceed in a very similar manner to the previous one, where we attack the hydrogen from that nucleophilic and basic double bond. However, because this conjugated diene is not symmetrical, which double bond do we attack it with? And the answer is, we can attack it from either. So in other words, we need to show both reaction pathways in order to get all of the products for this reaction. For the first pathway, let's attack that hydrogen from the furthest right pi bond. That, of course, will kick off that bromine. And as usual, whenever we use an acid, we are going to create a carbocation. So that's going to create a carbocation in the more stable allelic position. Following pathway 2, we're going to attack from the leftmost pi bond. Once again, that's going to kick off that bromine. And just like in the pathway above, we are going to form the most stable carbocation, which is again now going to be in this allelic position. To better your understanding, once again, I will draw in where we added those hydrogens in blue. Now from here, we have to recognize that because we have an allelic carbocation, that we have to draw our resonance structures. Of course, if we don't catch this right now, we can always catch it in step 4 of the problem-solving process, but I would rather take care of it as soon as I notice it rather than wait. So drawing in these resonance structures, once again I'll draw our arrows for the resonance in green to show the electron movement, and then I'll erase them when I move on to the next step of the mechanism. With the resonance structures drawn, hopefully now you can see that we have 4 pathways with which we can attack with the bromine anion. So let's draw that step next. Once we draw all of our arrows from the negative bromine to the positive carbocation, you can see the results on the right. Of course, I would have to mention the fact we have to check for stereochemistry in these products, and we should check for E and Z stereochemistry as well as Rns stereochemistry. In that very first product in the top right, we do have a stereogenic center. So we do have the carbon that is bonded to the bromine has 4 unique bonds to it. And again, because a carbocation is trigonal planar, we can attack from either angle, front or back, with the bromine. That's going to put this on a wedge or a dash. Our second product also has a stereogenic center. So once again, we need to put a wedge or a dash in that position. Our third product does not have a stereogenic center. That's because whether you go clockwise or counterclockwise around that cyclohexane, you encounter the same environment, so there's not 4 unique pathways there. The final product also has no stereogenic center where we added that bromine. When we check all 4 of the intermediates and products for E and Z isomers, we realize that only one of them has them, and that is this second one here. So when we have this double bond, that methyl group on the end of it could have been facing the other way. Once again, I'll draw where we had that hydrogen and that bromine, which stays either a wedge or a dash, in blue. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.